Welcome to another tutorial, and today we are going to learn how to use game components to manipulate geometry nodes in UPBGE. So let's get started. So I created this item with the geometry node setup. I learned geometry nodes yesterday just for you. And just saw some tips videos and watched a Ducky 3D video and then made my own little thing. So I'm working on a game and I need something that looks like an item that I can change. So came up with this cool little shape, and then I could use orange for attack power-ups and green for health and purple for status effects in the game, status items. And so yeah, so I made this little thing. It looks cooler from far away, so I'll render it from far away. That camera angle's terrible. Let's fix that right now. So we'll go here. And we'll go to our view, align active camera to view. And what's going on? Where's my camera? Okay, so my camera's way too far away to see it, so we gotta bring it in. So go, press E twice, zoom in until it shows up. And then we're going to go ahead and shrink this thing down some more and put it in place. All right. So what I did is I have this whole convoluted mess here that creates this energy fire image thing. And then I created these nodes here that basically will be what we'll animate with our script. So we got a scalar, which we'll probably not use, that's the base value. But I created a node called anim scalar for animating the scale, and seed animate for animating the seed. Just to go over what this does, so this node ID basically, these are all actually cubes, and each ID is an instance of the cube under the spreadsheet section. So I saw, just the values. And so, there's actually only 90. Oh, I guess there's only 98, but the highest value is 384, so I set it to 384 in geometry nodes. I set my max value for ID to 384. And so basically this object, the ID of the instances in the object goes into the ID section of this random value vector that basically manipulates the rotation and scale of these cube instances. And then I use these image textures that are generated by Blender. Used a Voronoi texture basically, and the seed goes to the W value here to animate it, and then the Voronoi texture basically distorts the cubes, and then they're recombined here in instance on point. So the is instanced on the different vertices of this cube, and then the geometry is joined. Let's try doing this real quick just to see what it does. Let's pull out another. See, I make it look weirder. Probably gonna ruin it. Huh, looks the same right now. Yeah. Okay, cool. I applied shave smooth, signed the material here, and then realize the instances so that they become like geometric shapes and not looking all particle-y. These are volume. This is actually a volume cube, and then yeah, output geometry. You could go look up tutorials on geometry nodes, but the point is basically when I move the seed or I animate the seed, it does some cool shit, right? So it creates an animation I can use to basically react to a player or something when the player's nearby. Try to remember what I think I was at seed 3 was the cool looking. Yeah, that's cool looking shape. And then I could add some emission strength to it so it glows better. Yeah, looks more organic and less cubey. And then also I got a scalar here that we can do. We can animate by manipulating the factor. So if we bring the factor all the way up, it's gonna morph away. And it does this kind of cool, like, and if we want to push it more, we can do it even more, and it gets bigger here. That looks neat too. So that could be our item. Let's scale it down a little bit. Get all the glow in frame. To do the glow, you go to compositing tab. And you add a glare node, set to bloom. I'm going to actually set to high quality, just see. And because this is a geometry node, it's pretty performant. Like if I press play, see we're in thousands of FPS with the OpenGL setting. So yeah, it's hitting 1200. So yeah, it's a good deal, right? So you get all that complexity with, but it's all instancing, so it's all on the GPU, relatively cheap. So what we'll do now is we're going to create a component to animate it, and that'll be it. We'll try and keep this tutorial short, because I know I have some long tutorials. So, first we'll go into Vim, and we'll write this script as geonodes.py. And we're gonna need BPY and BGE for this. So import BPY, import BGE, and next we are creating a component. So we'll do class. We'll call this geochange, and it'll inherit BGE types dot kx Python component. We could do some args to set initial values. So we'll do args. Do the standard one is active, so we can turn the component on and off. And then we're going to do go ahead and name it after the nodes we're going to manipulate. Anim scale. We actually don't need them because we'll set the initial values down here on the node. So we'll just set is active. And we'll do def start. Yeah, for those wondering, yeah, args is built into this BGE types KX Python component class, so this will only work with certain components. It works with KX Python component and KX game object from BGE. It's actually, args is actually, I looked in the GitHub and it looks like args is actually arg start, update, and dispose, the 3 functions of this Python class. They're actually coded in C++, it looked like, so, or C. Self.isActive is equal to args is active. Def update pass. And since it's an item, items you want to use the dispose function. So when the item's collider is destroyed, it'll do something. We're not doing that, we're just animating it today. But if you want a tutorial about, I don't know, controlling characters and switching to between the controller target between like the player collider and a menu system, and then items and stuff and arrays, let me know, because that's what I'm working on now. Alright, next, not a tutorial, I'm doing it for me, but I can show you if you want, you just have to ask. Alright, next, what are we doing? So, when manipulating anything in Blender using BGE, you need BPY, but also what you want to do is go to let's blow this up real quick. You need to go to File, or go to Edit, and go to Preferences. And under Interface, you need to make sure this Python Tooltips checkbox is checked. Because that's going to, the tooltips are going to tell you how to manipulate our geometry nodes. So for example, if I mouse over the things I want to animate with our component, right? We don't do it with keyframes, right? We do it in-game with code because you never know. Like, we could do an animation, create an animation on the timeline, and then play the animation from code. That can be a very useful way to do it if you have some kind of complex movement. But since we're just manipulating these floats, it's just easier to change the value in the code with the code. So, if I mouse over the factor here that animates this, right? If I mouse over it, it tells us down here in the Python, it says, Python, the value of this slider here is bpy.data.node_groups brackets geometry nodes .nodes anim scalar, right? And I named it anim scalar by pressing N and changing it here under name, right? Oh, okay. So .nodes .anim scalar .input 0 .default value. So that defaults underscore value, that's this factor slider right here. So we can manipulate this with code. And then also the other one, and actually this is the more important one because we're just going to animate. So we could do, this one is called bpy.data.node_groups, node_groups, brackets, geometry nodes, dot nodes, brackets, seed animate, dot inputs, bracket 0, dot default value. So you're going to find with most of your node sliders, the value you're going to manipulate is default value. So if you got a single integer here in your slider, that tells you two things. A, the type of it is going to be an integer, and also that that you're only going to be sending one integer value. If you go over here to something that's a vector, right? If I wanted to manipulate this random value here, that's it's just dot nodes random value, right? Its default value for this field is actually default value bracket 0, then 1 and 2. And what this tells us is this is actually a list or a vector 3. But you could actually input three value lists as a vector 3 into this. So you don't have to worry about importing the vector type for math utils, right? You can just use a list. And Python will change it. And it's actually not that much of a performance hit. If you pre-process as a vector, it doesn't really matter. Because I think the GUI actually converts it to a list before it brings it in. So, the type is a vector 3, and you could do that, but I don't know. I mean, unless you're controlling the vector 3 C class directly, that might improve performance if you have a lot of assets in the scene, but if you got just this, you don't need it. So, if we want to manipulate this would be a list of 3 values. This one here is a bigger node, so it's going to have more. So, this one, it has an inputs 1, has an inputs 2 with a value 0. So this one is a vector 3 or a list of 3 values. This one here is inputs 3, default value with the vector 3. Then each of these are actually inputs 4, inputs 5. So these resolution ones are actually single integer inputs. So these would be their own variables. These ones, the variable would be assigned to like a three element list. So the clue of how you program it is actually in how the node is laid out, if you can make sense of that. If you can't make sense of that, become a better programmer, because I'm not that good, but at least I understand. All right, so next we're going to go ahead and we're going to animate the seed. So first let's get this looking cool. So we're going to turn this back down until it looks cool. I like this shape here. All right. And then we can seed it. Man. So it does some. Yeah. And what we'd actually use the seed for is to actually pick different kinds of things we want to animate. Like this thing where it's small particles, we could scale it up, right? See, and then it, goes away. Like if we find one here, a seed here that's even smaller, like that, that's a good like transition for the item to disappear, right? So we could actually increase the scale of it on all axes, and then we can use our factor slider and make it go away. That doesn't look that cool though. It doesn't look as smooth. So I'm gonna undo until we get back to the shape I like. There we go. All right. So we'll go ahead and animate the seed here, or Yeah, let's do a ping pong animation of this. So let's increase the scale of these a bit, like that. Yeah. So what we'll do is we'll do a ping pong animation that goes back and forth between this and that. It'll ping pong back and forth, but it'll do it so slowly that it looks kind of continuous. So, let's bring back up the code. All right. All right, so first we need to create another function that's going to perform this. So we're going to do def we'll call this seed ping pong. Input self, because it's inside a class. And what self does is it basically makes the functions accessible from anywhere in the class. Like if I did it like this, it would only be accessible immediately after and not be executed. So yeah. It's in a class, has to be self. All right. So first we actually have to get, so this is going to be attached to this object. It's basically a cube. You see here, it's a cube, but it's got this geometry stuff on it. Like if I press tab, you see there's a little cube right there. That's actually, this is the vertice source, but the nodes are what making it look cool. So all right. There we go. So first we have to access the geometry node section of this object, and that's going to be under self.object.blender object. This is how you access the blender data of an object. And we'll do dot, and then where are you? So BPY data, so we need to do node groups. So is that going to work? Nope. So we'll say nm scale is equal to bpy dot data dot node groups, and we do brackets, then geometry nodes dot nodes, and the node's name, so nm scalar dot inputs 0. Now we don't actually want to do the last part of this here, right? We don't want to do dot default value because we need this data from the object loaded into memory on this variable before we can manipulate the subvariable of default value. So now we got that, and then we want to set our range. So this is where we're at 0 and it looks cool. So we want to first do is say if anim scale dot default value. Also, you notice that because these are a custom property of a node, right? They don't show up in the autocomplete of the Python stubs. So you have to trust the tooltips here. So, yep, default value is equal to 0.0, or let's do less than or equal to. It won't go lower than 0.0 because that's the lowest it can go, but sometimes with floats, there's problem with it not being absolute 0. So actually we'll do this. We're going to actually do 0.0.1. Less than or equal to 0.0.0.1. Because a float, one of the bugs of floats in all programming languages is that a 0.0 float value will actually be like 0.0000, a bunch of zeros, and then like 39. And so it doesn't absolutely equal 0, and so your logic might not work. So by doing this, we can make sure it's pretty close to 0, and the if statement will still work. So, all right. So if it's going to do that, and we're going to have it reference itself for its own logic. So we'll go ahead and do this. So we're going to go ahead and copy this. Oh. Or yank it. And we'll paste it. And what we're going to do is we want to move slow. So actually, let's go ahead and add another 0 here. And then we'll do anim scale default value plus equals 0.0001 if anim scale is that, else 0. So what we did was basically, you know, this is the badass way of incrementing values with logic in Python. You put it all in one line, right? You put your if statement after your change and the else. So what this translates to is we're going to increment default value up by 0.0001, this value right here, if anim scale is pretty close to 0. Else, oh, nope, that's wrong. So we have to set our maximum here. So this is where we set our maximum. I was thinking in the wrong direction. So what's something relatively same size? So that's kind of cool looking. So 0.250. So is less than 0.250. And we want to move even slower, so we'll do that. We'll start really slow. Also, because we're manipulating this thing in space, we may want to go ahead and add a delta time function. So let's do that real quick. Def delta time. This is a global function that's outside the class, so we don't do self. And then we'll do target frame rate, target FPS is equal to bpy dot data dot scenes we could do this bpy data or bg, let's do bg dot logic dot get current scene dot, what's this value at? Okay, so dot game settings. Is it gonna work? Oh, let's do it this way. Scene is equal to bge.logic.get current scene. Then we'll do target frame rate. Target FPS is equal to bpy.data.scenes, then bracket scene dot game settings dot FPS. So our target FPS is 60, but that's a logic FPS. That's not the FPS of our frame rates, because we have VSync turned off, so our graphics card can really, rip and really perform. But we're going to use delta time so the animation stays consistent. So we got that, and then we don't even need that because our logic tick is also 60, so we could do this instead. So let's do target FPS as our logic tick. So we could do bg.logic.get logic tick rate, and then our average FPS is equal to bg.logic.get average frame rate, and then delta time is going to return give me a second, I gotta look it up. I believe it's average FPS over, if I have these flipped, the frame rates are going to be weird. Average FPS divided by target FPS if 0 is less than average FPS is less than 10,000. We just need a high number. Else return 1. Let me double check if I did that right. Always look at your old scripts to make sure you did things right. Okay, it's target frame rate divided by. See, I did it wrong. That's why you always reference your old code. Alright. There we go. So there's our basic delta time function. And then what we'll do here is this will, and then we have to assign it to a uncalled variable. So we're not going to call it. So dt is equal to delta time, but we're going to remove the parentheses. So the function is stored in memory ready to go, but it's not called. And then we'll call it when we use it. So this will be times dt bracket. There we go. And then our next line will be anim scale so we want it to ping pong. So the problem is it's going to get stuck, so we need some kind of trigger. So we're going to do a ping pong variable. So self.ping pong, self.ping pong, yeah, is equal to false. And we'll say comments false is ping, true is pong. Okay. So then we'll do if not ping ping pong, and we'll do else. And then in here we're going to do if anim scale dot default value is greater than or equal to 0.26, then, oh, this needs to be self. Self.ping pong is equal to true. I'm going to change this to elif. Elif self.ping pong. That way if there's any edge cases, nothing will happen. All right. So anim scale dot default value minus equals 0.0001 times dt if anim scale default value is greater than or equal to 0.0. No, yeah, just greater than 0. There we go. And we'll do how many zeros? 1, 2, 3, 4, 5. 5, so we'll do 6 zeros. 6. Okay. Else 0, and then I gotta fix this. There we go. Then if nm scale dot default value is less than or equal to 0.0, six zeros and a 1. Well, the lowest value on this is 0.0, so we don't need to worry about that. Let's just make it 0.0. Yep. Less than or equal to 0.0. Self dot ping pong is equal to false. All right. So it's going to start with ping pong equaling false. Then this thing's going to start animating. When the factor value gets greater than 0.26, it's going to flip that ping pong variable to true. Then this code will kick in, and it'll start to go down the opposite direction. And then once it hits 0, ping pong will flip again, and it'll do this code. And so all I have to do now is self dot seed ping pong, and then we'll do if self dot is active, and we'll move that over. There we go. And why do I have an error? Because I have an I there. Okay. All right, cool. So we've created a delta time function, assigned it to an address in memory without executing it, created our GeoChange class, create our ping pong function to animate this, and then this should work. So let's attach it to the object. So we'll go to the Python tab here, go to add component. We got to bring in the script though, so let's go to the text editor, and we got to save it. Okay, and open geonodes.py. There's our code. Add, then we'll do geonodes.geochange. If I can spell right. Site is active. Let's get it nice and big. And I have to go back to, I have to get this thing set back to 0, so, or back to, yeah. So factor going back down to 0, we got our cool shape. And now we press play. It's doing something because our frame rate dropped. Did I get an error? No errors, so... Okay, it is moving. It's just moving way too slow. Yep. I'm not being dramatic enough, so... Let's see what factor we want to get. Okay. Let's try shaving some zeros off of this. Let's try that. And then Alt-R to reload. And play. There we go. Okay. So we're not getting exactly the logic. It is animating, but we're not getting the exact logic we want. So... And our frame rate's dropped a lot. It is a volumetric cube, so that's probably what's doing it. Why is it freezing? Okay. So let's see, what code did I do wrong? Let's try setting this to equals to 0.0. Oh, I see. I have all this extra crap in here. I screwed up my code with Vim. Okay, there we go. So increase, I don't know if we need this delta time. Let's try doing it without delta time. It probably might start going way faster though, because the frame rates won't slow down, but we'll find out. Oh. You're the cause of this. Ah. There we go. We won't be calling delta time, and we'll get rid of it from memory. See what this does. We may change this to else, so... Yeah, it's... Okay, is it ping-ponging? It goes... we could print the value to see if it ping-pongs. So... Print... Oh, do we get better performance? No, we're still getting 71. Okay, delta time's not affecting anything, and it's needed in case your player is playing on a laptop because they're cheap and don't want to build their own machine. It's building your own machine's cheaper than buying a computer. All right. So we're going to do print self anim scale dot default value. And we should basically see this number ping pong. It should go up, hit a certain value, then start going down. Oh, you know what? That might be the cause. Let's just go ahead and do this. Set it equal to 2.5. All right. See if that fixes it. Okay, we're getting error. Oh. Okay. Okay. So the numbers went all the way up to 0.25. So we have to do, and then they stop. So it's not doing the ping pong, it's just doing the ping. So if it gets to 2.5, what we have to do is, if it's greater than or equal to 2.5, set self.ping pong to true. And then if it's true, we'll go ahead and make this an else. We'll make it more definitive. We're only doing two things, so it shouldn't be buggy. Okay. Else. Anim scale value minus or equal to. And we'll do less than or equal to. Because floats are weird. Floats sometimes. I'm going to do this. There. Save. And we'll play. See if that fixed it. There we go. We got a ping pong. Yep. We're animating with our code. Sweet. Let's get a bigger look at this. Behold, I have animated geometry nodes with code in UPBGE. Don't you all wish you were me? Say yes. Ha-ha! Alright. So that looks cool. That looks like it'd be a good item to pick up, except the ping pong is too apparent. So we're going to actually go ahead and slow it down even more now that we've got it working. So let's add a couple zeros. We'll start by adding one. We'll add 1 0 at a time. Save it. Oh yeah, this is another. I think this is a girl's front line, or it might be a one of those Souls-like games, but it's a clock, so I think it's cool. And anime girls are great. Next. Okay, so we've saved that, and then go play. There we go, that's looking subtle now. We'll see how abrupt the ping pong is. That looks like an item you might want to find in an adventure game, right? Especially if it gives you like plus 50 strength to your plus 5 sword. Oh, the frame rate is staying the same, so that's pretty good. We should see what happens if we instance it, how much performance we lose. We have the max value yet. Yeah, we've already ping-ponged and we didn't notice. Alright, that's a good animation. Yeah, the player would be long gone by the time the animation finished. Cool. They'd have to really be looking at it to see it. Alright, we've made our power up. Okay. So let's see if we can get this more performant. Probably not, but we could scale it down. So like I'm working on a platformer game, so like scaling it down and playing. We still have the same frame rate. Why? It's because it's getting the... Let's try setting this as a constant. We know our frame rate is... We know our logic rate is 60, so we'll just do that. Yep, with or without delta time. Alright, so we got our animation. Let's work on performance real quick. So we can disable shadows. That'll help. We'll actually, at the end of the day, we'll probably turn this into a sprite. So it can be flipped through a sprite sheet. And then we'll apply the glare node to the sprite sheet to get the additive lighting effect. But ray tracing is disabled. Sample rate is 1. We could try doing standalone start. Okay, that's even worse. Might be the print command. Oh, the dependency graph is going off the charts. That's the source. So Blender's dependency graph is causing this. Alright. Let's try switching to Vulkan. See, the great thing about my tutorials, it could be about anything I want. I dare you. Oh. Let's try that first. Okay, that gave us 10 more frames, switching it to automatic from GLSL mode. Is it slowly going down, or is it holding steady? It's holding steady. Let's check Vulkan. Turn off anisotropic filtering under viewport. And then system. I'm not using my processor, and we're using CUDA. Okay, we'll try that first. We'll add our processor to the... Yeah, we're still holding around 80, just under 80. Now let's get this bigger again. So scale's not making a difference, so that's cool. Here's our animation. Well, we'll go ahead and try using Vulkan for performance. Vulkan, it'll be peaked at 60, but the load times will be less. So, save preferences. Save our project, close it, say hello to the anime girl. Bring it back up. Yeah, Vulkan is giving us 60 frames per second, but it's a solid 60. And the dependency graph went down, so it's multi-processing on the dependency graph. So this looks like it might be an issue with Blender 5. This might be a reason to go back to 4.44, 0.44, but it's working. We got animation with Python, with components. And we'll get rid of the print function. That'll be our last optimization. So print is gone. Save it. See if that fixes things. I mean, so it's not getting a float every time. Now it's in Vulkan now, so we can't see the performance increase. Let's go back. Open GL. Save, restart. Okay. Yep. It is what it is. Let's go ahead and push this a little bit. We'll duplicate this a few times, so we'll go here. See if this makes performance worse. Oh yeah. Okay, geometry nodes. Yeah, so geometry nodes are probably running on the processor. Yeah, the dependency graph went up by another 10%. We're down to 34 frames a second. Oh, samples are at 16. Let's get them down to 0. Now try. Yeah, that'll only give us a frame. All right. Well, we got our cool animation in UPBGE. All right, so You now know how to manipulate GeoNodes with UPBGE. So just quick review, and then we'll be done. What we did was we created our geometry nodes with these controllers that we named autoscaler and seed animate. We didn't animate the seed, but I don't care. And then we went to the value here, got it from the tooltips, put it here, assigned it to a variable. Then the default value variable at the end of it, we incremented if it's between certain values. And then we flip our ping pong variable between true or false, so it switches between these two if statements. And this is the result. All right, so now you know, and knowing is half the battle. Have a great day. Bye.